Hi, welcome to the Signal Path. In this episode, I'm going to do another product review for you guys, and I'm really excited about this one. I'm talking about the new Keithley 7510 7.5-Digit bench multimeter. This is a high-performance instrument, and Keithley advertises this to have noise performance that exceeds some of the 8.5-digit multimeters that are available on the market. It of course has the same LCD screen, runs the same operating system as the new source meters which I have reviewed in the past. It supports the same scripting language as well as the Kickstart software, and I will demonstrate that, which is a fantastic tool. It gives this unit quite a bit of extra capability. And of course, it has a broad range of applications and measurement capabilities that's already built into it, which we will go through as well. Of course, it's not cheap. We were talking about something just under 4,000 US dollars. So it better deliver all the kind of different measurement capabilities and performance and so on that you would expect for this much price. It is the fastest multimeter that I have ever used. It can sample up to 1 million samples per second in digitizing mode, and the update rate on the screen is unbelievable. You really have to see it to believe what this unit can do. So I really enjoyed using it, and we're going to do a bunch of different experiments with it, starting from some basic functionality and just getting familiar with the unit, and then we'll dive into some more advanced experiments, and we'll do a little bit of a quick teardown so we can take a look at inside of it as well. So let's get started. Now, before we get started, I just wanted to show you the different measurement ranges this instrument supports. Now, I'm not going to go through the data sheet because it's available online, and I recommend that you definitely go and look at it, because it is in there where you see the accuracy, the resolution, the tolerances over time and over temperature, and all those very important parameters for such a high precision instrument, and they're all of course guaranteed by Keithley. So make sure you look at that. But just a very brief overview here. You can see that under DC voltage we can measure down to a 10 nanovolt and all the way up over 1,000 volts. Under DC current we have a picoamp of resolution here, and we can measure up to 10 amps. The resistance range is amazing because it supports a full 1 ohm resistance range, so which means that under 4 wire measurement you have 100 nano ohm of measurement capability, which is quite amazing. Now, the capacitance can measure all the way to 1.2 millifarad, which is okay. It basically covers almost everything. The frequency, it stops at 500 kilohertz. I'm a little bit surprised because it has such a strong digitizing function. I'm not sure why they stop at 500 kilohertz, but it would have been nice if it went over 1 megahertz. But anyhow, you have from 3 hertz to 500 kilohertz measurement capability. And under digitizing voltage and current, you can see the different ranges. And you will see some of these in action, of course, when we're going to do the experiments and everything in detail, but definitely check it out because it's pretty interesting to see what a 7.5-digit meter like this is actually capable of, and especially in terms of calibration if you're looking to do very sensitive measurements. So here it is the unit with the case taken off. It's very straightforward, just one screw and the case directly slides off. And you're looking actually at the bottom of the instrument, so it's upside down. And the very first thing to notice is that the design is quite similar to the source meters. They've gone with this dedicated, essentially DSP operating system board, motherboard, which runs everything that is associated with the user interface applications. All of this is contained in here. It has two processors on it. It has a Spartan FPGA on it, as well as the GPIB controller, a whole bunch of flash memory, a few unpopulated components, bunch of DC-DC power supply, the backup battery, and all the interfaces. You have Ethernet, you have the triggering, you have the digital IOs, you have the TSP interface, and so on. Everything is of course on this board, handled through the digital board here, and they connect the digital board to the analog board, which is on the other side, through this daughter board interface, which has a bunch of optocouplers on this side of it, just outside of the camera view, which have cutouts inside the PCB. Everything is done, of course, the right way you'd expect that from Keithley. And this kind of design, you can see that what they've done is, because they're running the same operating system across their source meters as well as this multimeter, and I'm sure for their future instruments that they're going to release in this whole modernizing the interface to the touch screen, they're going to be reusing this type of design. On this side you also see the LCD cable that of course goes to the front LCD. Here's the DC-DC power supply and some other boards to handle the connection to the rear panel and so on. So it's very nicely put together. Again, I don't expect anything but very good design from that aspect. So I'm not going to go into too much detail of it because I know you want to see more of the instrument in action. But if you flip it over, we will see something also quite interesting. Here we go. This is the back of the unit, and you can see the back of the unit is completely covered by this massive PCB shielding the unit entirely. And this is all planes of ground that you can see covering, and they've gone through the trouble of connecting that to the body of this fuse holder. And this body of these fuse holders for the two ranges of the fuse, these things are custom machined. These are not some parts that you can find, because these are absolutely massive, and as you saw when I was showing the back of the unit, but you can see now the inside of the unit as well, where that component is. So in order for us to see more of what is underneath it, I'm going to have to take this board off. One other thing that's a little bit unusual is that there are no holes on top of the case of the unit where the fan is. So this fan is essentially blowing into the top of the chassis that's on top of it. So I'm not sure how effective this fan actually even is, considering the fact that the chassis, there is the chassis, and it sits like this. You can see that there are going to be no holes where the fan is. So this is definitely an unusual design decision. I wonder why it's not sideways, or perhaps why the case, the surrounding case doesn't have holes on it to support the fan. But anyhow, I'm sure they've done their thermal analysis, or perhaps this was something that they realized they needed too late into the design and didn't have the sufficient resources at that time to take it into account. But anyhow, let's go ahead and take this panel off and see what's underneath. And here's the view of the unit with that PCB removed. The PCB is just sitting up here because I don't want to disconnect the fan cables completely. But you can see the fan was blowing over this area, and that this area appears to have some high power ICs there, and that's most likely where they want to make sure that the temperature doesn't exceed a certain amount. And all the covers that you see here are covering the portions of the circuit where you don't want the fan to blow air over them, and you want to stabilize the temperature as much as possible in order to ensure that the ambient doesn't have a strong effect on the performance of these as the temperature drifts. You can see various resistors here, precision resistors, and there's some more in there. And this unit actually has glass resistors, glass covered resistors, which can be etched, laser etched after they've been assembled, because obviously the glass is transparent and they can fire laser into it and etch it and measure it and so on. It has a whole series of really fancy analog circuitry on the PCB, and you can see that the multi-stage converters and amplifiers and so on are all covered. Now, I don't want to remove these to show you what's underneath them, mostly because I'm doing this teardown right now before I do the review, and I don't want the calibration of the unit to be in any way in question or affected by me taking it apart and having access to the components that are shielded. So we're going to have to leave that for some other time. But here's the 3.5 amp fuse. You can see now the cover that goes around it to ground it, to isolate it even further. Of course, that makes sense considering the fact that you want this to go down to extremely low currents. So the 10 amp, 11 amp fuse, it's not actually, does not have that protection because it doesn't need it. Once you're in this range, you don't have the lowest measurement of noise that you require anyway. And here's the back connectors there. So everything is beautiful. I mean, this thing is a work of art, and the people who design this really understand how these instruments work and how they should be designed. They have quite a bit of experience in it. So I'm really excited to continue using it in the lab and showing you some of the experiments that I've designed for it. So let's put it back together and get back to some testing. So let's start with the back of the unit before going to the front and turning it on. At the back we have the Ethernet port, USB port, the digital I/O ports, as well as the TSP link, which is for scripting language, and you can daisy chain, of course, the units, and we'll talk about that. Here's the GPIB for backward compatibility, the power plug, of course, and here's the external triggering input and output, which can be used again with other units to trigger the unit and synchronize their measurement capabilities. Here's two massive fuses, wonderfully done again for the 11 amp and 3.5 amp range, easily accessible from the back. And here's the back terminals. Now, the back terminals differ from the front in the sense that the back terminal actually has the 10 amp range. Unfortunately, the 10 amp current measurement capability doesn't make it to the front panel, because in the front panel you only have these 5 connectors. And instead of the location of this one, you have the button to select between front and back connector. That's unfortunate. I would have liked to have the 10 amp range in the front, but hey, it's at the back of the unit, you can still access it. They did it for real estate reasons. So you can see it's pretty straightforward at the back. So I'm going to turn it around, hook it up to the computer, connect it with TSP link to the source meters, although you can't actually use the Kickstart software with the TSP link daisy chaining source meters and multimeters. So you can only daisy chain multimeters in the Kickstart software. Anyhow, that's one limitation that they have put on these, not to be able to mix and match devices in the Kickstart software. Anyhow, we'll get to that. So here's the back of the unit, pretty straightforward. Just turn it around. And here we have the front panel of the instrument, and you can see that it looks very similar to the Keithley source meters, the 2450 and the 2460, which I've reviewed. And of course, that's no accident. This is part of the strategy for Keithley to create a signature look and a unified, coherent experience when you jump between any of the recent advanced instruments that have this GUI interface with the LCD screen. They all run the same operating system and so on. That's really important because it really does make a difference in the experience you have when you use these units. On the left side, we have some of the basic buttons: home, menu, quick set, and help. The help is very useful because it gives you a live help on whatever function or setting that you're trying to figure out at the moment. And on the right side, you have enter, exit, function, and trigger. These buttons are essentially here to allow you to access those settings without having to go through several steps on the LCD screen. So they've done a very good job on choosing what buttons to put on the outside. And this is the same again to the source meters. You have, of course, the USB in the front. You have a hard power switch here. And on the right side, as I said, you do not have the 10 amp input current range, but you do have the 3 amp. Instead, you have the front and back terminal switch, which you can press. And this one is actually quite stiff on this unit. And you also have the selection rotational knob here, as well as a button that's behind it. Now you may ask, why didn't they just shift all of these up and then put another 10 amp input here? And the reason is because on the source meters, this is where the output on and off button would be. And what they want to do is they want to create only one front panel. They don't want to manufacture multiple different ones with different molds and different designs and different PCB at the back and so on. This is really to reduce cost. I suspect that's the reason why they've done it. So let's go ahead and turn it on and see what happens. Now you can see the boot up time as well as how it reacts. Of course, the buttons all light up, and you can see this F setting here, which says that this is a setting on the front panel. There's a bunch of other lights up here which will turn on if you're on remote and LAN and so on. And there it is, and you can see this is the main screen that you would face. And look at ridiculously fast this is. This is automatically jumps on the volt select mode, of course, and it's on a 100 millivolt range. And you can see these 3 zeros are, of course, in the 100 millivolt, and then the rest are just smaller and smaller decades of the voltage. And of course, it's again 7.5 digits. That's why you have so many digits here. And the last couple of the digits here, just cannot see how fast they update. It's quite incredible. By default, it powers on having the number of power line cycles to be 1, which you can of course change, but the speed, just never seen anything like it. I do want to point one thing out, that Keithley is no stranger to extremely fast instrument. This is the 2015 THD multimeter, and this is another 6.5 digit meter that also has THD capabilities from Keithley. This is a pretty old unit, and you can see that it does update very, very quickly indeed. The reason this is counting up is because its input impedance is very high, and it's collecting charge essentially, but if you connect it to a load, it will go away. But anyhow, there's another example that they have a long history of creating extremely fast multimeters. So the LCD screen on these units is the part of the instrument you're going to have to interact with the most, because almost all the functions are set through the LCD, unless of course you're programming it remotely. So the GUI is very important, and it has to be very smooth and easy to use, otherwise the experience would be frustrating. When I initially got the 2450 and 2460 source meters, I was a little bit reluctant about the LCD, but after using those units for some time, it really works quite well, and they've done a really good job on programming it. And what they've done recently on top of that is that they have updated the software of all these units to a more unified, similar look, as well as they have significantly improved the speed and how smooth the interface reacts. For example, just take a look at how nicely this instrument reacts to being, swiped left and right, and I can go fairly quickly or I can go very slowly, and it works really well. It's very responsive. It almost feels like a smartphone in terms of how quick it is. And that's very important, because you don't want to be waiting for this thing to load, or you have a frustrating experience when it misses, you're touching it and so on, and you don't want that. And it doesn't do that as far as I can tell from my experience using it. And now the source meters look exactly the same also, which is great. So the very first screen is of course all the different functions the unit supports, measuring voltage, measuring current, resistance and so on, as you can see. And these buttons are actually the same size as the buttons that are out here. They're not tactile, of course. They don't have a tactile feel to them like these ones do, but that's something that you might want to have to get used to a little bit. But if you use your cell phone all the time, you're going to be pretty easy to use. Now, if I swipe to the left, I get the secondary function. Here in the secondary function, you can choose what you want to measure as a secondary display at the bottom here, and that means that you can measure voltage and current at the same time. Now, if I go ahead and enable that, listen to the unit. Of course, that's because the unit has to change the relay in order to jump between the secondary measurement of current and the primary measurement of voltage. But that's not because it has to do that because it's doing two different measurements. It has to do that because the range of measurement is different between these two. If you change the range of the secondary measurement to a different range which matches the voltage, in that case it doesn't actually have to switch the relay. Right now there is nothing connected to the instrument, and the automatic ranges on these two by default are different. Now you don't want to leave the unit when the relays are clicking, because they're clicking a couple of times a second because it's so fast. And that means that it will really age those relays very quickly, and Keithley also doesn't want you to really do that. You can of course always change the range in order to fit your needs. If you change the range, you may not always be at the optimum range you want to be in, but then the relays wouldn't switch and it would be much more practical in using the secondary function. If I swipe again, I get to the remote program text here, and we'll take a look at that later. I've shown it also before in the source meter. Now if I swipe to the right, I get to the main settings of the currently selected function. Right now the currently selected function is voltage, so I can enable other things. For example, auto zero is enabled right now, the input impedance is 10 mega ohm, filtering is off. Right now the number of power line cycles is set to 1, I can select it and set it to, let's say, 10, and if I set it to 10, of course the sampling rate drops significantly, and that's because this has to take much longer for it to collect the data, but then you get much more accurate result because you decorrelate yourself more and more with the power line cycles that you have in the instrument. Now if I go to the right again, I will see of course the graph, and the graph has been plotting as a function of time. You can see here is 161 seconds, here all the way 564 seconds, and you can see this at this point right here is where I changed the number of power line cycles. So you can see the signal went from jumping around much more to being far more stable, and that's, again, you can see one of the advantages of doing that. And right now there's nothing connected, so keep that in mind. And if I go on the right again, now I get my statistics, and these statistics can be cleared. Of course, you can see I have 28,297 readings. I can clear it, and you can see that if I clear it, I'm getting an average reading voltage of 77 microvolts. There's nothing connected again, a minimum, maximum, and so on. Of course, I can also always just swipe it down, and the numbers then get gigantic, and the unit moves down here, so you can see it even from further away if you're in the lab somewhere, not close to the unit. And you can also bring it up and down. Now if you go in different menus, you have little buttons here, and these buttons will do different functions. So depending on the menu you're in, you're going to get that button. So it's actually quite small, so sometimes you might accidentally hit the other one. But if I select the first one, if I can get it, come on, there it is. You can see that here's the calculator settings and the calculation settings on here. I can go home again, it will take me back here. If I click on the other one, I can go to the measurement setting. That's one of the complaints I have about this in terms of the GUI, because these are really tiny and really close. And right now I'm sitting actually in a very awkward angle because the camera is in front of the unit, so it's very difficult for me to reach over. But this would help significantly if they were just even a little bit further apart as opposed to being right next to each other. So if I want to click on the calculator setting, there you go. If I want to click on the other one, there you go, measurement setting. So it's okay. It can be a little bit annoying if you want to go. Of course, you can always go through the menu and get to the same settings as well. But other than that, everything else is really nicely accessible. It's just those two little things that can be a bit frustrating. You can also press the menu button and it takes you to all the different menus. You have categorize, measurements, views, trigger, script, and system. You've seen me do a lot of these on the source meter, so I don't want to go into too much detail not to waste your time if you've already seen them, but all of your settings are already here. And we'll take a look at some of the plotting functionality as well here, for example, the graphing and the histogram and so on. But before we do any of those, let's just do one really basic measurement. Let's just measure a reference voltage. Now, I have verified that this thing obviously meets its specification and all of that. I'm not going to do that on camera because I think it would be a waste of your time. We're just going to do a very quick measurement, but this of course meets its calibration, claimed calibration settings in its accuracy and so on. You would expect that from an instrument like Keithley. So I'm not going to strain test it for that. It's more interesting to do different kind of experiments with it at this point. And here we go. I have connected my DMM checkbox directly to the Keithley 7510, and we can go ahead and measure our 5-volt reference voltage, and I'm going to turn it on, and there it is. And you can see that obviously it reads very close to 5 volts. The temperature in the lab is a little bit higher than the calibration temperature of this box, as well as the calibration temperature of the Keithley, but once you wait about 30 seconds or maybe a minute or so, this thing actually settles to about 5.00007, which is, you know, pretty close and exceeds the expectations anyway. And it works quite well, and I can obviously do things like, as you saw, go ahead and change the number of power line cycles. I can make relative measurements and so on, and now I can take a look at the graph that is being recorded and so on. Pretty really straightforward stuff. One thing I want to point out about the interface is that you have to be a little bit careful. Here you can see that the DC volt is selected. If I select, for example, let me go ahead and turn this off, and if I select, for example, resistance, you can see that it will highlight it. Now, this is actually just a highlighted. There is no distinction between highlighting a button and selecting a button. This is something I've suggested to Keithley, and they're going to implement that. So by swiping over a button, you can actually highlight it without selecting it. So if I do this, you can see that I'm selecting the AC voltage. I'm highlighting it, but I'm actually not selecting, and I can do the same thing over the DC voltage. So it's a little bit confusing because you're looking at this like, wait a second, this should be measuring DC voltage, but it says mega ohm. So it's a little bit confusing in that regard, and they're going to fix that. I suggested that they use 2 different colors for what they call focus as well as selection. Anyhow, that's a minor detail. They're looking into that. They're quite responsive into adopting any good GUI ideas that you may have. And of course, if I select it properly, you will see the voltage. So it's really easy to do. And let's do one other measurement. Let's just do a 4-wire measurement on one of the resistors, and then we'll get into some more interesting experiments. So here I have a 0.01 ohm resistor, which is a 1% resistor, and it's intended typically for calibrating voltage sources and current sources and so on. And you can see that it actually has 4 wires coming out of it, and it's specifically done this way so you can do a 4-wire sense measurement on it. So what I have done currently is that I have not set the instrument to measure in 4 wires. Actually set to measuring 2-wire like this, and of course I'm measuring not just the resistor itself, but I'm also measuring the contact resistance from all the connector here all the way to the resistor itself. And as soon as I switch it to 4-wire, I have automatically connected it, and check it out, 0.01000. It's really accurate, not just the instrument but also the resistor itself. It's almost dead on, and it's far better than 1% that it's advertised at. This is a very expensive resistor, so I expected it to be quite good, and you can see that it performs really well. And this is one of the really big advantages of the Keithley itself, of course, because it has a full range 1 ohm range setting, and that allows you to go all the way down to these really small resistance values that you would want to measure. And I show a demonstration of a particular example of that for, you know, a problem that you might come across, and we'll see that later, but just wanted to quickly show that indeed you can measure resistors really well. So let's go to the other extreme end of the measurement scale. Here I have a 1 gigaohm resistor that I've put into this simple apparatus that goes from banana, and then I've kind of connected it to these connectors here. And I've done this so that the wires are very short and they're not subject to being moved around and picking up charge from the environment. Measuring a 1 gigaohm resistor is quite difficult. Typically need a guard voltage and all that, which I don't have, so this is still not completely ideal, but you're dealing with very small currents that needs to go through this resistor in order to be able to measure the actual resistance. So it's going to be quite sensitive. Now nonetheless, and also remember that because of the center conductor of these 2 wires going through a piece of Teflon with the ground around it, there is some resistance associated with that piece that's going to appear in parallel with that resistor as well. Something to consider. Nonetheless, let's go ahead and do this measurement. By the way, one other thing that this has been doing is that the highlight actually completely disappears now. I'm not sure why it wasn't doing that before. This is the first time I see it. So now you don't even know what is selected. The focus and the selection is gone. So for example, I click it again and it's back now. This is something that I've reported to them. I'm sure they're going to fix it quickly. Just keep in mind, look for the update on this. So there you go. Now we can see that the measurement is being shown. Let's go ahead and change the number of power line cycles to a few more. Let's go with 5 so we can get a slightly more stable measurement here. And let's go ahead and clear our active buffer here. And you can see that we can clearly read the measurement here, of course, 0.997, and that already exceeds the 1% rating of the resistor. So it's quite a good measurement for a 1 gigaohm resistor. And you can see the average value is being reported at 997.12 mega ohm, with a standard deviation of about 188 kilo ohm. Like I said, this is still not an ideal measurement setup because we don't have a guard voltage and all that. And I can demonstrate that this is not ideal. For example, if I go to, where was our plot? There it is. And if I maximize our plot over here and I go under scale, and let's look at all of our data at the same time. And just by bringing my hand close to it, you can clearly see that I pick up on the measurement a variation. I'm not touching anything. This is just me injecting charge into the system. And since we're measuring very small amount of current, and if I remove my hand, you can see that the measurement is far more stable. And this is a representation of some of the difficulties that come along measuring such a large resistance. So here I'm interested in judging the capability of the Keithley 7510 to measure very small amounts of current in preparation for the next experiment. Now, in order to supply the current, I'm going to use the Keithley 2450. Now, the 2450 as well as the 2460, these instruments are designed to generate very small amounts of current very accurately. So it's not a big task for them, but it is quite difficult to measure with a multimeter very small amounts of current. Now, I have connected the output of the source meter directly to the input measurement current of the Keithley. Now remember that even in this short cable with the setup that I have, there is still going to be some electrons that are going to escape, and that's going to mean that the current supplied by the 2450 isn't exactly, not all of it is exactly going to go directly to the Keithley, and this is going to be important at very small amounts of current, as we shall see. But nonetheless, right now I have the 2450 set to 1 milliamp, and 1 milliamp is a very large amount of current, of course, and I can go ahead and enable the output. And there it is. We can see that the Keithley says 1.00000, so it's really close to 1 milliamp. Now, the source meter is reporting 0.99998, so there is a tiny difference between the two. Of course, this is well within specification, no problem there whatsoever. But we can go ahead and make the current even smaller. So let's jump from 1 milliamp all the way down to 10 microamp. Now, 10 microamp is the full-scale input of the Keithley at its smallest current range, which is 10 microamp range, and you can see that we are reading 9.39s after that, and we are seeing 9.999 over there. So they're again really close to each other, but that's nothing. We can go, of course, much smaller than that. So let's keep going from 10 microamp. Let's jump all the way up to 10 nanoamp. That's a factor of 1,000, and then you can see again we have no issue. And let's stabilize the measurement a little bit. Let's take a few more power line cycle measurements. Let's set that to 5. And then go back. There it is. You can see that that's the number we're looking for. You can see that it's jumping very close between 3 nines and then 1 over there, and we have 9.999 over here. So again, no problem at all. Now let's really push it, and let's go all the way to 0.1 nanoamp. That's 100 picoamp of current. That's a really small value. Now we're looking at this digit essentially. Of course, our measurement is going to jump around because there is going to be uncertainty and noise, as well as the fact that the setup isn't perfect, but we should be able to go ahead and go into our statistical measurement here and clear the buffer and just look at this number, which is the average number. And when I bring my hand to it, I can disturb it actually. So we're going to wait a little bit and see what that's going to kind of settle down to. So we see about an 85 picoamp measurement, which is really impressive. We are supplying about 100 picoamps. Some of it is escaping, of course. Some of it is escaping from the setup. But we are measuring with a fairly good accuracy. We have a standard deviation of about 17 picoamp and 85 picoamp current in this crude setup. So that's going to be pretty useful for the next experiment that I have. We're going to measure the conductivity of a flame. So here's my setup for measuring the conductivity of a flame, and it's actually really simple. So if you pay close attention here, I have two parallel plates, and in between the two parallel plates I have a nozzle which I can put some butane gas through and then set it on fire, and it's going to create a little tiny flame in the middle that's going to look like a candle flame, except it's going to be burning butane as opposed to wax. So by doing that, if I were to place a large voltage across these two parallel plates and measure the flow of electrons, measure the current, that flows between the two plates, I can then compare that current before and after the flame is there, and I can then make a comparison, a relative measurement with regards to how much extra current I get when the flame actually is present. Now normally a flame burning in atmospheric pressure like this, in with the 20% oxygen and so on, of a butane gas is not plasma because it's not hot enough, but it still will have ions in it which are charged, and those charged ions are going to move in the presence of an electric field that's going to form between the two plates, and that's going to create obviously a flow of current. Remember, the current will go from the positive to the negative, but the electrons will go in the opposite direction. So the electrons will be aided by the conductivity of the flame and will jump across that and then jump to the other plate and create current. Without the flame, the electrons would have to jump a much wider gap, and that's the effective conductance of the environment between the two plates will therefore be a function of whether the flame is there or not. And then depending on how much flame there is, you're going to have a different conductivity. Now normally you would have to do this experiment with a very large amount of voltage between the two plates, because the amount of current is going to be rather small, especially because the plates are so far apart. But because we have a 10 microamp range on this instrument, we can put very little voltage. By little I mean in comparison to relative to the amount people normally put. So I can put, let's say, a couple of 100 volts. I'm going to start with 250 volts, and then we can measure the current. Now the circuit is broken through the multimeter in a sense, so you can see that the positive cable comes through here, then goes through the multimeter, and the current measurement comes back to the other plate. And because the resistance of the multimeter is very low, you're going to basically get almost all the voltage across the two plates. And this liquid that you see here is liquid butane, and that tube that goes down comes from underneath here, and then that's the tip where the flame will be formed. And I'm going to have a lighter here like this, and then we're going to turn on that flame and be able to measure the conductivity. Now obviously you have to be very careful. I've made sure that there is a sufficient insulation here, even though this is only 250 volts at very low currents at DC. You still have to be careful. And I'm applying the voltage here using my Stanford Research PS350, which has actually gotten quite a bit of use since I repaired it, and you can see that it's set to 250 millivolts. I've limited the current to only 1 milliamp, which is actually really large for this, and so on. So we can easily be able to do this measurement using this instrument. All right, here we go. Let's go back over here, and let me go ahead and just increase the number of power line cycles just a little bit, so that we can have just maybe a slightly more stable measurement here. And perhaps I can go to, there you go, the current measurement here. There we go. So we can have something like that. So you know what I'm going to do, I'm also going to clear the active buffer. There it is. So now we can see that the current is basically very, very small, and this is just some charge being picked up by the plates, and there's lights around all over here, and that's normal because these are exposed, of course. Now I'm going to go ahead and enable the 250 volts. There you go, and you saw that spike of current that passed by, and that spike of current is to be expected because there is going to be a spike of current to charge the capacitance that is formed between these two plates, and that initial current was captured by this instrument, and you can clearly see it. And if I were to go back and look at the full result, I will be able to see that value. Here we go. I can actually go into the plotting function and look at that. You see that? Isn't that amazing? That is the spike of where I actually have done this. This is my hand coming closer, but this is the part where the capacitor was being charged, and these little spikes, as you see, is from my movement around here. So you can clearly capture a very, very small amounts of current, which is quite amazing, really. So there it is. Now we have a constant steady state current of about 4 nanoamp going through it, which is a lot more than it was when the voltage wasn't applied. And that's to be expected because there is some electrons that are escaping from the surface of the plates even when there's no flame, of course, and that is a steady state current that represents the conductivity of the air gap that is between these two. And you can already measure that, and that itself is pretty amazing. Alright, so there's our steady state current, and I'm going to do my best here and reach across the camera and enable the gas here and set it on fire. And then you can have your eye on this value and the plot, and let's see how much that changes. Here we go. There it is. And look at that. Isn't that amazing? We have now a huge amount of increase in current, about a factor of 50 from what we had before. We have now about 0.25 microamp or so, and you can clearly see it in the plot. Now look, I'm going to make the flame small and large by adjusting how much gas goes with my thumb there. See, small flame, large flame, and you can clearly see that the conductivity is a direct function of the size of the flame. And we can measure that without any difficulty with only 250 volts. And this is already way above the sensitivity of the instrument. I can go even further down in voltage and have no problem and be easily within the dynamic range of this instrument. This is really amazing. This having a low noise floor and a large dynamic range and very small current measurement capability, as well as having 7.5 digits, is what distinguishes very high-end multimeters for scientific experiments as well as electronic experiments, because a lot of times when you're doing physics experiments you do want to have something that's extremely sensitive like this one. And this is one example. I have another example that I'm sure you're going to like about the other upper range of the measurement capability, but you can clearly see it that by doing that I can change the amount of current. Now I'm going to try and hold it with one hand here, the flame going, and I'm going to increase the voltage now from 250 to 500 volts. So I'm going to double the voltage. And I don't know if you noticed that or not, but if you pay close attention, you'll see that the flame actually is deflected towards the negative plate. Now, normally the ions produced in a flame should be statistically distributed between positive and negative. In this case, it's not the case. It seems like the ions are mostly positively charged, so they're going toward the negative plate. And look, the current has gone up significantly, and this difference you see here, this spike over here was when I changed the voltage, and that little spike over there is when the flame was temporarily sucked toward the plate. That's really cool that you can actually see that effect. Now I'm going to also show you one other thing, which I'm going to directly connect the two voltages across the plate, so we can crank up the voltage above the rated value of the floating ground of this, because remember, these voltages are floating with respect to ground, and you're not supposed to put more than 500 volts in a negative terminal. And I in fact made a mistake and I put 5000, and the self-protection of the DMM kicked in and protected the input, and nothing happened to the multimeter. It went back to being exactly the same, calibrated in the same way. So I actually caused the 5000 volt spark inside it, and it did nothing to it. That's really quite amazing. Anyhow, so I'm going to disconnect it, then I'm going to put more voltages so you can really see the flame move to one side. And this is just the experiment for the sake of completeness. I'm going to put 1000 volts on the plates. The multimeter is no longer connected to the plates. And check it out. You see how the flame gets sucked toward one of the plates? Let's go to 1500 volts. You can see even more, and if I go to 2500 volts, you can see how much it's being pushed. You can almost see the wind of electrons pulling the flame to the left. That's really cool. I'm gonna now go all the way to 5000 volts and check it out. You can clearly see, actually hear sparks forming, which is because there's so much current being sucked to the plate. Now, like I said, the ions are supposed to be distributed evenly, but they are not, and I have an idea of why that is, and it'll be make an interesting discussion in the comment section. But here's an example. Oh, there you go. I just melted the plate and it's melting the insulation. There it is. But anyhow, you got an idea of what's going on. So that was one experiment that I really wanted to show you. Let's move on to the next one. Of course, one of the main advantages of having a 7.5-digit multimeter is the fact that you have so much resolution and so much dynamic range. The idea is to be able to see very small changes of voltage or current around a very large value, and this is what I'm kind of demonstrating here in this example. I have connected a lithium polymer battery this way, this one right here, which is a 3-cell battery that's in parallel. When it's fully charged, you're expecting to see about 4.1 volts, which is exactly what we're looking at right now. And I'm just directly connecting it to the input of the multimeter, and I'm looking at the voltage. Now, normally with a 6.5-digit or 5.5-digit multimeter, you don't have enough digits to be able to see this last final digit here, which we're looking at. Now, that digit is going to slowly change, and it's going to slowly drop as time passes. That is essentially the discharge, the internal discharge rate of the lithium polymer battery. With a 6.5-digit meter, you'd have to wait a very long time before this digit right here, this 5, will actually change. But if you look carefully here, as I'm talking, you've noticed that it's been slowly dropping, and that's of course the internal discharge rate. Something like this is very useful when you want to monitor this type of behavior, something that you want to monitor fairly quickly or very slowly changing events around large voltages. Now we are sitting here at a 10 volt range. Of course, if I set this up to 1000 volt range, then you can see again small changes around the large voltage, which can be helpful, especially in physics experiments and things like that. Just wanted to give you a quick view of what that would look like. So one of the most compelling features of this multimeter is its extremely high sample rate, and they've taken advantage of that by implementing a digitized voltage and digitized current capability. Now within these two capabilities you can set your sampling rate, you can set how many samples you want to store, you can plot things and do all kind of fancy triggering, and we'll go over that during a testing of a module that I have here. But I wanted to go over a couple of little things and show you a few observations that I've had here. So under digitized voltage, which is what we have here, we can of course set, as I was mentioning, your sample rate and your trigger and so on, and your AC or DC coupling. So for example, let me just change the sample rate from just to be 1000 here for our purposes. And once you're in the digitizing function, you have to select your range. So for example, like I have ranges that change by a decade. So if I go to the 1 volt range, then you actually have a 20% over range, which means that you can capture signals which are as large as 2.4 volt peak to peak. So you can go 1.2 volt and minus 1.2 volt, and it will fit within that range, which is fantastic. So you have 2.4 volt of a full scale input here. And if I go to a 10, then it will be 24 and so on and on. So once you are in this range and the instrument is sampling, it's basically going to collect 1000 samples, wait, and then re-trigger because it's in continuous triggering mode. It's going to continuously capture and display the waveform. And here's the waveform right here. And if I go onto the plotting, and I can just do that so that it's doing a full scale there, you can see that there is a plot just continuously being captured, and the scale here on the left is very small, of course, because this is just the noise of the instrument itself. What I've done at the input is that I have terminated the input into a low impedance of 50 ohms, just so that I don't have a lot of noise being injected into the instrument while I'm moving my hand around it. Otherwise, other than that, there is no reason. You can also, this is basically the noise of the instrument by itself. Even now, if I bring my hand here and bring it close to the terminal, as you can see, obviously I'm going to inject noise into the unit. Now if I go back in here and I go and clear the buffer here, you can see that it's taking 1000 measurements at a time, just like I told it, just like I asked it. And the peak-to-peak voltage it is measuring is 300 microvolts with an average of minus 1.6 microvolt, which is about 0, and a standard deviation of 40 microvolt. That's just the noise of the instrument itself. That's perfect, and it looks good, and I think has a reasonably low noise for a 1 volt full scale. But let's just go to 10 volt, and you can see that the noise will grow, obviously, because we've moved a range a decade up. That's to be expected. But as soon as I go from 10 to 100, then I see this, and that is a little bit unusual because it's a periodic noise, and its amplitude is quite a bit larger than the difference between the 10 volt and 100 volt scale, and I can actually hear the relay inside the unit change. So I've asked Keithley about that to see what this is from, and it's a little bit puzzling because it is a bit larger. Now if I go over here and I clear this, you can see that the peak-to-peak noise here is 100 millivolt, which is quite a bit larger. Now again, the fact that this is a periodic noise is what is of concern to me, and we're going to look at the FFT of all of these functions. Now this instrument internally doesn't have FFT, and it's begging to have one, and I'm sure that they're going to implement it, especially once you see what you can do with the FFT and the examples that I've prepared. It has to have an FFT function. It can be extremely helpful because the dynamic range is so huge that in order for you to see multiple signals at the same time, you have no choice but to look at it on a dB scale. So that should be pretty interesting. Now, how do I collect data? Well, we're going to use the Kickstart software in order to collect some data from here and then take a look at it. So even though there is no input, I want to capture just the noise of the instrument and do an FFT analysis on it, and we can compare it at different scales, and that should be interesting enough. So let's take a look at the Kickstart software. And here we have the Kickstart software. I apologize for filming this screen. I just want to give you a quick idea. You've seen me use the Kickstart software, especially during this source measure unit review, but basically this Kickstart software, which is a free software, is a platform for you to collect data and set configuration, set up sweeps and so on from a variety of instruments that Keithley has provided, especially the latest instruments that use this new LCD GUI. And I use this all the time, especially with the source meters, to set up sweeps and so on. But essentially, it's a one-to-one interaction with the unit, and the nice thing about it is that it makes it very easy for you to extract data from the units, which then you can send to a different medium for processing, and that's what we will be doing here. You can see that the main a screen here has all the configurations of the unit, and there's a drop-down menu which you can set every different setting that Keithley DMM supports, along with the digitizing functions, capacitance, voltage, everything that you would want is here. And once you select the appropriate function, then you can set all the sub-parameters of that exactly like you would from the front panel GUI. And once you are set up and you're happy with it, then you just start a test, and it will do the test, collect the data, and store it. And it will collect it in these sheets of data, look like Microsoft Excel essentially, and then you can export them into CSV format or even Excel format, which again you can use for further processing. Now I've also collected the data here, which I will talk about afterwards. This is a very large 240 volt peak-to-peak 8.5 kilohertz signal. We'll talk exactly how that came about, and we'll talk about the result of that. But right now, what I was interested in was to capture the digitizing outputs from the instrument at different scale settings, and then look at the FFT result of that, so we can investigate that ripple noise that we were seeing to see how it shows up on the FFT domain, which will give us a little bit more information. And after that, we will do a large dynamic range digitizing test. And after having exported the data to MATLAB, I should be able to bring that up so we can take a look. And here it is. So let me explain to you what we're looking at here, because there's quite a bit of data here. This is the 4 spectral content of the instrument without any signal applied to the input, just terminating into 50 ohms. This is when the scale is set to 1 volt full scale. This is 10 volt, this is 100 volt, and this is 1000 volt. And immediately by looking at this, you can see that something happens between a 10 volt and a 100 volt scale. The 10 volt scale has a very flat, reasonably flat quantization noise, and you can see it doesn't have a lot of spurious tones in it. But as soon as you go into the 100 volts, it's true that the noise floor moves up by a factor of about 20 dB, which you'd expect because the scale has changed by a factor of 10, but then you get all these extra tones that appear. And in fact, look at the fundamental, the main most dominant tone is at 13.67 kilohertz, just like I said before. Now, normally this is not a big issue, but if you're trying to measure very large dynamic range signals and you want to look at this spectrum, then you would have this spurious tone somewhat interfering with your measurement. And this is one of the things that I wanted to point out. But in reality, if you look at the dynamic range you have from these, it's huge, because you're looking at a very, very large range of signals that you can simultaneously measure. And I'm going to describe to you a setup I put together right after this, and then I'll show you the FFT result of that, so you can see the incredible dynamic range. But this is something that I would like to see if it's resolvable, or if it's something that's to be expected as part of the instrument design. Either way, it's something to keep in mind if you're going to do this type of analysis on the FFT. Again, I'm really pushing the instrument here, and I expect a lot from it because it is a high-end instrument and it is pretty expensive, so that's why I'm putting it really under the microscope to show you guys that we take good care on looking at the performance of the instrument. But otherwise, it's pretty amazing, as you will see by the next experiment. I want to do another quick experiment to show you the extreme dynamic range of this instrument to be able to capture signals in digitizing current or digitizing voltage mode. And I've put together a very simple setup here, and I'm going to briefly explain it. On the right side here, I have an 8.5 kilohertz signal that has a very large signal amplitude, 240 volts peak to peak of signal swing coming in from this side. And on the left, I have a 400 kilohertz signal that has a very small amplitude, only a couple of volts peak to peak. Now they both come into this breadboard, and I have some voltage divider resistors there to combine them together and add them essentially linearly together before they go onto the multimeter. Now in the process of adding them, I am further attenuating this signal such that its amplitude is absolutely tiny when it's combined with the output amplitude of the 240 volt peak to peak. So we're talking about a 240 volt peak to peak signal at 8.5 kilohertz and a few millivolt signal at 400 kilohertz simultaneously being sampled by the multimeter. Now you can imagine, in order for you to be able to capture both of these signals simultaneously, you'd have to have a low noise floor as well as a huge dynamic range on anything that has to capture such a large dynamic range signal. So a few millivolt, 240 volt peak to peak together going into the multimeter. And just as a quick example, this is where the 400 kilohertz signal is coming from. The 240 volt peak to peak signal is coming from a high voltage function generator on the other side of the lab, which is just outside of the camera view. Now if I zoom in onto the screen, I've already set up the instrument in digitizing the voltage as we saw before, And yeah, it's just capturing the signal continuously. Let me just center the screen here. And you can see that I have the range set to 100 volts. Of course, the range goes all the way up to 1000 volts, in which case it would be even more interesting, but I cannot go all the way full scale in 1000 volt here in my lab. That's why I've chosen the 100 volts there. So you can see that I'm capturing everything just as we saw before, and I can go ahead onto the graph settings. And if I can get that damn button, that's one of the annoying things about those tiny buttons. Even if they make it a little bit larger, I think it would be a huge help. There's the curve right there that is being continuously sampled, and you can see clearly the signal. Obviously, you're not going to see the couple of millivolt signal at 400 kilohertz because it's so small, but it is in the signal, and I'll show you how we can view it. So you can see at the very top is 126 volts, and at the very bottom is minus 132 volts. So this indeed is a full-scale signal that is 20% above the 100 volt range of the multimeter. That's a 20% overload that's allowed on the meter beyond the range that you select, which is fantastic. So 240 volt peak-to-peak signal you can clearly see. And here is the captured plot of the signal I just talked about. You can see the 240 volt peak-to-peak signal. Obviously the very small signal you cannot see because it's embedded in there. It's much smaller, but I have captured that and I've looked at it onto the spectral domain, and we should be able to make some interesting conclusions about that. So let me bring that up. This is the old one that we looked at, and this is the other plot that I wanted to show you. So let me talk about this because there's a lot of information here. This again is the output spectrum of the instrument while the two signals are simultaneously applied. Obviously at the bottom we have the scale in kilohertz. It goes from 0 to 500 kilohertz, the 500 kilohertz being the Nyquist rate when the sampling rate is 1 million samples per second, and on the left we have the signal amplitude in dB volts, and I have already normalized it to 0. So in reality this is more of a dBc result because we have 0 here and everything else is in dBc essentially because it's already normalized to 0. Now here's my main tone that I injected myself at 8.5 kilohertz. It is at 240 volts peak to peak, and you can see that it's the most dominant tone. Its second, third, fourth, and fifth harmonics are all there. Because the signal is so much larger, that spurious tones that we saw before are embedded somewhere in here and they're mixing with these other tones. So they are there, but nonetheless they're not interfering too much with this result. This behavior, this skirt behavior that you see here is actually the phase noise of the function generator. This is not from the instrument, this is from my function generator because it's a very large signal function generator and it's very old. It's actually quite noisy in terms of its jitter. And this is, you can see this phase noise, which is pretty amazing to see. Remember again, this is a multimeter we're looking at and not a spectrum analyzer. It's not a high-end oscilloscope and so on. This is a multimeter with a very high dynamic range digitizer, and this is what we see. So we see all the harmonics, we see the skirt from the phase noise, and if you go all the way out here, there's a tone here. This tone at 400 kilohertz that I have purposely chosen its amplitude to just peak above the other tones nearby. That's the other tone that I've injected. Its amplitude is 100 dB in volts quieter than the fundamental tone that's here. This is 240 volts peak to peak. This is 2.4 millivolt peak to peak, and I'm capturing them simultaneously, and this shows an enormous dynamic range between these two tones being simultaneously captured by the multimeter, which is very impressive. Now some of these tones are the spurious tones that are caused by the instrument itself, and if they go away then you have even better result from here. That's why I'm really eager to see where those tones are coming from. But this demonstrates the incredible dynamic range we're talking about, and this is why I was saying that this instrument has to have an FFT function, because that's the only way you would see such a huge range. It has to be on a dB scale. You cannot otherwise see a factor of 100,000 in amplitude. So pretty amazing and pretty interesting. But anyhow, this is really a deep analysis on performance. Let's do some practical example. Let's look at a DC-DC converter and let's capture some waveform. So next I'd like to take a look at this DC-DC converter module. This is a really old AT&T module that takes in 48 volts and puts out 5 volts all the way up to 10 amps. These things are typically used in optical communication modules and systems and so on. And so what I want to do is I want to take a look at this. I want to look at its startup behavior, and I will look at its noise at its output, the ripple, because it is a DC-DC switching converter. And I want to take a look at it under two conditions: when it's loaded and when it's unloaded. So the output, which is taken on this side, actually splits into here into two, and I can then add a load to it. This is a 5 ohm load, so if this is 5 volts, we're looking at 1 amp of current. When the load is disconnected like it is right now, you will get no current at all, so it will just be 5 volts under no load, and then when we load it will be 1 amp, so then of course the behavior is going to change depending how much load there is. And in order to power it on, At the input of it, the 48 volts is going to be provided by the Keithley 2460 source meter. At the bottom, the DMM7510 is going to be used to look at the output voltage. So right now, if I enable the source meter to 48 volts, it's going to be pretty straightforward. There it is. We're going to get 5 volts coming out, which is exactly what we would expect. It's a fairly stable 5 volt. It's a reasonably good DC-DC converter. So you should have no problems displaying that. So let's focus in on this display here. First, let's just take a look at it under no load, see what we see, look at the histogram of the output voltage, and then I like to take a look and see what the startup behavior looks like. Alright, in order to see the histogram, we just go under menu and then we click on histogram, and there we get a histogram of data. Let me just clear the buffer so we have a brand new measurement, and here it is, and you can see that it is building a histogram of data. The scale at the bottom here, you can see the minimum scale is 5.01980 and the maximum is 5.01983. So it's a really narrow histogram, measuring really close by, and you can see that it's going to continue building the histogram data over there. I can zoom in and out. For example, like this, I can see more bins, I can zoom out further, I can change the amplitude. I can basically do everything you would expect. And if it's saturated at the top, you can see that it shows that little highlighted region, which I hope is showing up on camera. That means that the histogram is peeking outside of the screen, which I like quite a bit. Very simple, nice way of displaying that. And if you mess up the scale, you can go ahead over here, and then you can of course change the scale in any way you want, or you can just go on the histogram and press that. And press that, and then it will show you just the histogram again based on this normal value. So I'm going to go ahead and clear the data one more time so you can get an idea, and you can see the histogram being built right over there. Now I can go ahead and change and put the device under load like so, and we can go ahead and clear the buffer one more time, and we can see once again the histogram. Now you can see the values have shifted down significantly because there's some current being drawn, of course, and there's some IR drop. But if you notice, you can see the histogram has gotten a bit fatter, meaning that its distribution has extended beyond where it used to be. The range is now larger, and that's to be expected because you're going to get more noise coming out of the DC-DC converter when it's under load. Now, the best way to see that would actually be by looking at it directly on the digitizing function, which is what we're going to do next. And here we are directly in the digitizing function. You can see the output is at around 5.0 volts, and this is the waveform that's coming out of the instrument when it's not loaded at all. So we can go under the plotting function over here, and we can zoom in like so, and we can clearly see now the switching behavior of the DC-DC converter is very clear on how much ripple there is and how much what the frequency of oscillation of the DC-DC converter is. And we can actually do some more interesting things here. So let's say I focus here. Let me click on the trigger and make it a trigger manual. And now it's manual trigger. Every time I press it, I'm going to get a new trigger function. So now the waveform is going to be nice and steady. Of course, I can always look at the entire captured waveform. I'm capturing 1,000 samples. You can clearly see the behavior. So let's zoom in again, and like this, and keep it here. Now at the bottom, I actually have multiple menus. Right now, the menu is only showing the scale. It's saying that it's 1 millivolt per division, centered around 5.015 volt. You can see that it tells you which buffer you're using. It says what the timing scale is 30.97 microsecond per division. Very nice. If I go on the left, it's a legend on the x-axis and a y-axis, which we have not set anything. There's only one y value, which is the default buffer 1. Which is what we're using, so I haven't defined any other buffers. If you have multiple buffers, you're going to get multiple waveforms. You can compare them. There's just no end of what you can do here. This is just a quick overview, of course. So we're going to go to the right this time. Now the buffer is going to tell you the statistics right here. So it says what the minimum, maximum value, the standard deviation, and all the information, and the average, of course, average value of 4.9968, which is what you would expect. Now if I go one more time to the right, now I get my cursors, which is actually really easy and very fun to use on this instrument. So let's say that I'm looking at this. Now if I press this, I get vertical, and I press again, I get horizontal, and once again I get both. Now what I can do is I can grab these, and they leave this little shadow behind so you know where you're going. So let's say I want to measure the timing between these repetitive pulses, and I'm going to put that right there. There it is. Now it tells me that the delta x is 15.63 microsecond. That's the repetition rate of those pulses, which is of course a function of the DC-DC converter's behavior. And I can also move this one down here and move this one right there. It's actually already in the right place, and it tells me that I'm looking at a ripple that's about 8.9 millivolt peak to peak, and that's the behavior of the waveform as we expect from a DC-DC converter. And if I go on and apply continuous measurement, it will keep those cursors where they are. But you can see that my two cursors up and down really do contain the signal as we would expect. Now that I'm looking at this, I can actually go ahead and add the load live and see if the ripple gets larger, because that's one of the difficulties with DC-DC converters, that once they're under load, they actually can become noisier because of the switching transient behavior of the DC-DC converter. So let's go ahead and add the load, and here's our load, and I just added it. Now, of course, I'm going to have to rescale that and check it out. You can clearly see that the swing, the voltage swing has indeed become larger. You now have more noise than you had before. It readjusted my cursors. It's already at 12.08 millivolt per division. It actually doesn't even fully cover it. So I can go ahead and extend this a little bit further. There it is. So we're looking at 15 millivolts, almost doubled from what we were looking at before. And if I were to trigger this one more time, do a manual trigger and focus in once again, you can see the switching behavior much better and the ripples that you would expect from the DC-DC converter under this condition. So you can, right on the screen, put cursors, measure the behavior, look at the deviation, look at the standard deviation and the histogram at the same time, directly with the buffer that you store. You can store this value, you can keep it in a buffer and then recall it and have it overlap another one. There is just so many interesting things that you can do. Now, having said all of that, we also have the capability of actually defining much more interesting types of trigger. So if I go over here, I can go on the setup trigger menu, and over here I can define a trigger to be the trigger key. It can be an external digital bit, which is very useful. So if you have an external signal, you can use an external digital trigger to tell the instrument to make repetitive measurements, and the instrument can then report back and say when the trigger event is completed. This way you can synchronize the multimeter with other external pieces of hardware. For example, we're measuring and characterizing components in a factory and so on. Very, very useful. There's just so many cool things you can do. But for our purposes, let's set up a waveform trigger. Now, a waveform trigger is going to look very similar to what you've seen in an oscilloscope. You can define a waveform trigger to be an analog edge or analog pulse or a window type behavior, and this way you can capture transient effects just like you would capture on a multimeter, except with the added huge dynamic range of the multimeter itself. So let's define an analog edge like that, and now that we have an analog edge, it's telling us how much to weight and so on, which we're going to leave all that at default. It's going to be on a rising edge, and I'm going to set that value to be 4 volts, and I'm going to turn off the source meter at the top so that the DC-DC converter is actually fully turned off. It is right under load right now, so the load is connected to it, and it's going to wait for a trigger to hit 4 volts. Now if I go on the graph, and I'm going to remove these markers for now, I'm going to say initiate trigger model. Now it's going to initiate the model that I already defined. I'm going to press that to get a full screen. There it is. So it's continuously capturing data. Of course, this is off. This is why it's at 0 volt. And there is my trigger line right there. It's basically waiting for the voltage to cross the 4 volt line in order for a trigger event to happen. And it is in a continuous loop. So let's go ahead and enable the power. There it is. And voila, there you go. You see, it captured our rising edge. Now I can go in and really take a close look at this and see what happened to the behavior and check it out. We have so much dynamic range that I can zoom in and further and just completely see exactly what the overshoot value is. There it is. Now I can go back, enable my markers. I can see how long it takes for the overshoot to settle. Let's say I'm satisfied with this. Now I can see exactly that it takes about 281 microseconds from the peak of the overshoot before it settles back to 5 volts. I can enable the horizontal and I can see how much overshoot I have. There it is. I'm looking at an overshoot of about 200 millivolt, which may or may not be a problem in your application. But this is so useful to be able to do all your sensitive measurements directly on the instrument itself, and I'm pretty happy with it. It's very cool that you can do this. And remember, this is I still have the entire waveform, all of it, at my fingertip. Right there, the slow, I can measure the rising behavior, I can measure the ripple after it's settled down, I can see how much overshoot, all in one screen. And you can see it's pretty easy to use. I'm really impressed with these functions. I hope that they keep adding more and more functionality. These things have just a crazy amount of potential. Now, one of the features of frequency measurement that multimeters have that people care about is how small the signal can be before the multimeter is no longer able to measure the frequency. Here I have a 10 kilohertz sinusoid signal coming from one of my synthesizers. You can see that it's pretty accurate, 10.00005 kilohertz, and right now the amplitude is 100 millivolt peak to peak, so it's 0.1 volt peak to peak, and I'm going to continue to decrease the amplitude until we can no longer measure it reliably. So I'm going to go to 70. This is 70 millivolt peak to peak. You still have no problems. 60 millivolt peak to peak, 50 millivolt peak to peak, and it still has no issue. 40. There it is. Oh no, it's still okay. 30 millivolt peak to peak. This is now 20 millivolt peak to peak, and one more time, 10 millivolt peak to peak, still has no issue. I actually cannot get smaller than this on the multimeter, but you can see that it's no longer as stable as it used to be. It's jumping around. But this is a 10 millivolt peak to peak signal at 10 kilohertz. Let's change the frequency, and let's go from 10 kilohertz, let's say, to 50 kilohertz, like that. You can see that it jumps to 50 kilohertz. It's still 10 millivolt peak to peak. We can also try smaller amplitudes. Let's go to 1 kilohertz, like that. And you can see that it's beginning to make a little bit of mistake. So I'm going to go on to the amplitude one more time. I'm going to increase it to 20. You can see that it's a little bit more stable. So you can see at lower frequencies, it requires actually a little bit more amplitude. Now we are at 50 millivolt peak to peak, and it's just at the edge of working properly again. So its measurement amplitude is going to be a function of the frequency, but you can see that even with very, very small signals, you should be able to make fairly reasonable amplitude measurements, which is pretty good. So here I have the instrument set to measuring diodes, and here it is. You can see that by using this function we can measure the junction voltage on various semiconductors. Now normally on any measurement that you do, you can set any limit, so you can have measurement limits set up to tell you if your measurement is outside of a desired range. Now for a diode, that range is automatically set for you in advance, and you can see the limit 1 lower value is 0.3 volts and limit 1 higher value is 0.8 volts. Right now it's telling us that the limit 1 has failed, of course, because there is nothing connected to the terminals of the multimeter, and as a result we have an overflow, and therefore the limit is failing. You can actually set more than one limit inside the instrument, and you can program the instrument to react to limit failure in many different ways: visual, audio, trigger events, and so on and on. Quite complex stuff can happen. So here I have a Zener diode, and we can connect the Zener diode in a forward bias fashion to the multimeter, and we should see about 0.7 volts, as to be expected. There it is. This is the forward junction voltage of this diode, and you can see that it is slowly counting up, and that's because this is a thermal effect. The diode is warming up because we're putting 1 milliamp through it, and that's why you're seeing the voltage change as a function of time. Perfect, no problem. We can also go ahead and actually reverse bias this diode to see the Zener voltage on it. There we go. If I can see reaching across the camera here. There we go. There it is. And here is the junction breakdown, Zener breakdown voltage. It's about 1.9 volts. Now, because we have control over how much current we're putting through the diode, I can change that. I can change it from 1 milliamp to 100 microamp. And check it out. You can see a different junction voltage because we are right on the curve of the Zener breakdown voltage right there. And that's why the voltage is such a strong function of the current. I can also even go to 10 microamp for a very, very small amount of current. You can see that the voltage is now 0.95 volts. So this is pretty useful to be able to change the bias voltage of the diode. It's too bad that it's not more granular, but you could potentially sweep that voltage and actually get a voltage versus IV characteristic of the junction that you want, which is kind of funny to do with a multimeter. But anyhow, you can see that it's pretty capable, you know, to expect, of course, something like this. You can change the number of power line cycles and all that, but pretty straightforward and useful, and you can see an example of the limit fail test. And for those of you interested in measuring large junction voltages like this blue light emitting diode, no problem at all. Here's an LED with 1 milliamp of current, 2.6 volt forward junction voltage. So it's well capable of measuring large junction voltages. So let's try some scripting example. Here I have an Ethernet cable that has a short in it. Now I have introduced a short in this cable manually. It's around 6.2 meters, 6.3 meter from the input of this side of the cable. That's where the short is, and it's just wound up right now. The short is right over here in this area. Now normally if you want to find a short in a cable, if the cable is buried or is in a wall or behind something where it's not fully accessible, it would be very difficult to have to dig the whole cable out and find a replacement. It would be much better to estimate where the short is based on a couple of different measurements. Now, sometimes for RF and microwave cables, you can use a network analyzer to find exactly where the short is. But anyhow, aside from that, by measuring the resistance, assuming a uniformity in resistance in the cable, you might be able to estimate where the short actually is. Now, in order to measure the resistance of the cable, you need a piece of it like this, for example, that I have taken. You can see in this piece the end of it is shorted together, and then you have two terminals here. So if I measure the resistance of this piece over here, and I know the length of this, I can calculate the conductivity of the cable, or the resistance per unit meter of the cable, and so on, and then measure this cable and estimate where exactly the short is in terms of the length of the cable. Now, this is possible with this meter or any other very high sensitivity meter, because these resistances are very small, obviously. So you want to be able to make precision resistance measurements in order to be able to make a proper correlation and find the short. Now, on top of that, aside from the fact that this meter has a very sensitive range, it has a 1 ohm full scale range, it also has the scripting capability, and I thought would program this whole procedure directly into the multimeter. So the multimeter is going to ask the user, okay, connect it to this. Now that you've connected it, okay, connect it to this, and it's going to read all the values, calculate everything, and just tell us where the short is in the cable. So that should be pretty interesting, and I've already written that code. It only took about a couple of minutes. It's really pretty straightforward, and it's going to automatically walk us through that. So I'm going to focus here on the screen so we can see what the code is going to do. Then I'm going to execute the code and walk us step by step. All right, let's go ahead and execute the script. There it is. So now the script is going to ask me, enter the reference short cable length in millimeter. Now I've already measured my cable, and I'm going to enter the value. It's a 300 millimeter cable, and the unit is in millimeter. That's fine, perfect. Now I press OK, and now the instrument is asking me, connect the reference shorted cable to the DMM. Okay, I'm going to do that. I'm going to use 4-wire measurement, of course, because we want to make a very sensitive measurement. We want to de-embed all the cables. That's pretty straightforward. I've already connected it. I'm going to press OK on that. Now it's going to say, you can see that it did a measurement in the background already. Now it's going to say connect the DUT shorted cable to the DMM. Okay, no problem. We're going to disconnect our reference short cable, and we're going to connect the multimeter Kelvin clips directly to our suspect cable. And then I'm going to press OK, and check it out. It did all the calculation. It's telling me that the reference resistance is 0.152 ohms per meter, and the short is suspected to be at 6.3 meters. And like I said, the short was at about 6.2 meters or so. It's pretty close. It's really amazing. If this was a buried cable and you wanted to go and find it, this would be a huge help. And check it out. The resistance of this cable of the short is 0.96 ohms, so we're still actually in the 1 ohm range, and you can see how many digits we have there to work with. Now, this is a really simple demonstration again that we can easily do much more complicated scripting that you can program to do, and not just interact with the DUT, but also interact with other instruments through the digital IOs that are available at the back. So a quick example, let's do another scripting example and then move on. Now, for the capacitor's measurement capability, I thought that we would make our own capacitor. This is a little capacitor that I made, whose dimensions I've controlled very carefully. This is a 150 millimeter in this direction and 55 millimeter in this direction capacitor. Now, its dielectric is made of a material that's in the family of PVC type, polyethylene perhaps, and this is an example of that. You can see it's clear plastic, and its thickness I've measured very carefully to be just under 0.5 millimeter. So now that I know the dimension of this capacitor, and since I know the thickness and everything, and you can see that I've soldered 2 wires, one to the top plate and one to the bottom plate, I should be able to calculate the theoretical value this capacitor should have. Now remember that the equation that describes the power plate capacitor is just epsilon A over D, which is basically means the area divided by the thickness times the dielectric constant of the material. Now, you have to be careful with that, because that does not take into account the fringing capacitance that exists between these two plates from the bottom to the top that extends outside of the capacitor, and that fringing capacitor is going to have the dielectric constant of A roughly about 1. But the material itself, the dielectric constant of this plastic is obviously going to be different. Now, since I thought we can calculate this capacitor by theory, I can write a script such that the multimeter would then return to me the dielectric constant of this material, and I thought that would be pretty interesting, the relative dielectric constant, compared to, of course, to air, to vacuum actually. So we should be able to easily do that and write a script that asks us for the capacitor dimensions, and then it will give us the dielectric constant. So let's give it a try, see what it looks like. So let's go ahead and run the script one more time in this new script that I prepared for the capacitor measurement. And here we go. So now the instrument is going to ask me for some information. The very first thing it's going to ask me is the dimension of the capacitor in the x direction. Now I know that that's 150 millimeters. We can enter that. Now it's going to ask me the y dimension. We know that also it's 55 millimeter. Perfect. And it's going to ask the dimension, the thickness of the capacitor dielectric constant that occupies by the capa. Alright, let's go ahead and run the script. Here we go. There it is. So now it's asking me, the code that I wrote is asking me for the dimensions of the capacitor. So the dimension in the x direction, we know that it's 150 millimeter. Perfect. It's going to ask the dimension in the y, we know that's 55 millimeters. And now, of course, the thickness of the dielectric material, and that I said is about half a millimeter. Now we're going to press OK, and it's going to ask connect the DUT capacitor to the DMM. I'm going to go ahead and do that. It's just off the camera. There we go. It's connected. Now it's going to basically do the calculation and give me the dielectric constant. We're going to say OK, and here we go. Check it out. Pretty awesome. So the capacitor is measuring is about 0.4, 0.5 nanofarad, and the dielectric constant is going to be about 3 to 3.1. Now this capacitor is very large. It has a large area. It's just hanging in the air, so it's quite a bit actually susceptible to picking up stuff from the environment, but that's okay. For our purposes, this should be perfectly reasonable. So you can see that it's giving me a dielectric constant at about 3, and I double check then some of these PVC materials can indeed have that dielectric constant around 3. So it seems to be quite accurate and seems to work just fine. And this is just a very quick example. Now that you have this, you can, for example, write a code that tells you how much you need to trim a capacitor, or you can have a code that continuously measures the variable capacitor that you're adjusting, and then once it's within a certain limit, it gives you an audio response, and you know it's good. You move to the next part. So it's perfect for automation. This scripting is truly a powerful tool that Keithley has enabled with not just a multimeter, but the source meters that I've shown extensive examples of. I really like it. And there is just so much more that I can do, that I can show you with this. The manual for this instrument is over 1,000 pages, and it has so many internal options and features and capabilities that you can use. Just as a couple of more examples, for example, in the DC voltage or in any of the measurements, it supports a really wide range of secondary functions. You can have your measure your DC voltage and have all of these secondary functions available, as well as, of course, digitizing voltage and current that you can easily apply at the same time. It supports a really interesting measurement of ratio, where you can apply a signal to the input and a signal to the sense, and this will give you a ratio of those two voltages. Extremely helpful for fine-tuning and adjusting and figuring out, especially if you're working with DC-DC converters and so on, to see the ratio between the input and output. And I can just keep going, and there is so much that you can do with this instrument. But in the interest of time, I hope that what you saw so far gives you a good idea of what you can do with these. As you know, these reviews and preparing them, designing the experiments take a lot of time, and I hope that they are beneficial to you. If you do happen to purchase one of these because you saw this review, let Keithley know that you enjoyed this review. I don't get any of the cut of the sales or anything like that, but it helps me have a good relationship with them. And about the couple of issues that I raised, the noise that I saw, the digitizing voltage in the high ranges, and a couple of the GUI bugs and so on, I've reported them, of course, and they're going to look into it and check it, and I will update the review with annotations and so on once I hear back from them. But overall, I really am very happy with this instrument. It's become basically my favorite multimeter, but of course it is a very expensive unit, so you have to really be needing to use these advanced features to justify the cost. And if you need it, then there's really nothing else like it. And it's one of the meters that I go to first whenever I have a doubt in a measurement. So pretty happy with it overall. Hoping to see it improve continuously with more software updates and GUI updates, and I'm sure they have a lot of interesting plans for it. And if you like the review, definitely rate it, leave a comment, let me know what you think. If you have any questions, ask, and I'll be happy to test it and quickly get back to you. Until next time.